to another trainML tutorial. trainML is a GPU as a service platform specifically designed for deep learning. Our platform lets you get up and running on GPUs with just a few clicks without the need for managing servers, learning a new framework, or enduring a lengthy software implementation. In this tutorial, we will walk through how to use trainML training jobs to run a parallel model architecture search on the ImageNet dataset using a PyTorch model. We will use the ImageNet training code from the PyTorch examples repository to train ResNet 50, VGG16, wide ResNet 50, and alexnet models in parallel and compare their accuracy. trainML training jobs are ideal for this case, as they allow you to run one or more GPU-enabled workers on the same model code and dataset with configurable training commands for each worker. To get started, click Create Training Job on the trainML platform dashboard. We will enter PyTorch ImageNet Architecture Search as the job name and select RTX 2080 Ti as the GPU type. We can optionally add more GPUs per worker or more working directory space quota if desired, but we will leave these as the default for now. In the data section, we have the opportunity to add one or more datasets to the job. Since we are doing our architecture search on the ImageNet dataset, we will add it from the public dataset list. Public datasets like ImageNet are provided by trainML at no cost. As you can see, the dataset is over 150 gigabytes, but our worker disk size is only 10 gigabytes. When using the trainML provider, the dataset storage allocation is independent of the job, so you can reuse the same dataset over and over without paying additional storage costs. Since this is a public dataset, you don't pay any storage costs at all to use it. Since training jobs don't have an interactive interface like notebooks, we need to specify where to send the results of the training job when it finishes. The results could include the model artifacts, the training logs, and any other information your training code saves to the output directory in the job environment. In this case, we'll use the trainML local connection capability to have the job workers send their output directly to a directory on our laptop. In the model section, specify the URL of the PyTorch examples repository. In the workers section, we're going to try 4 different architectures, so select 4 as the number of workers, and keep different command for each worker selected. We will enter the command for the first worker to train using the ResNet 50 architecture. This command is rather long, but there are 2 reasons for this. First, since we are using someone else's training code, we have to work around its capabilities to get it to do what we need. Second, it is a good demonstration of the flexibility that you have when crafting a command for a worker. Essentially, anything you can do in Bash, you can do in a worker command. To break down the command more specifically, the first thing we are going to do is change directories into the trainML output path environment variable. This is one of the trainML provided environment variables that help you direct your code to the right locations in the job execution environment. For training and inference jobs, the trainML output path environment variable will be set to the directory that will be exported to the output location we specified in the data section. The reason we are changing into that directory before running our model code is that the PyTorch example code does not provide a command line argument for changing the directory to save the checkpoint files, and it defaults to the current working directory. By changing the current working directory to the output directory, we will ensure that the checkpoint files get included in the results that the worker sends to us when it finishes. The next portion of the command actually runs the training code in Python and provides some of the hyperparameters as command line arguments. This command also makes use of the trainML environment variables, one that represents the directory the model code gets loaded into, and the other that represents the directory the selected dataset is loaded into. In other words, this portion of the command says, use Python to run the main.py file in the ImageNet folder of my model code with the runtime arguments that follow. The location of the ImageNet dataset itself is passed as a positional argument. The last portion of the command captures the output of the training code and saves it to the train.log file in the output directory in addition to printing it to the console. Although you can download the worker's logs from the trainML platform directly after the worker completes, this can be a good way to ensure that this data is saved alongside the model artifacts wherever they end up being stored. Now that we have our command set up, we can copy it to the other 3 workers and change the architecture that each worker will train on. Click Next to review our job and Create to start it. Once the workers get provisioned, they will automatically start training. You can view the job logs for all 4 workers in real time by clicking the View button. This way, if a worker's training isn't progressing the way you expect, you could preemptively stop it. Since we configured the workers to save their output to our local computer, we need to connect to the job so that the workers can send their results back to us. To do that, click the Connect button and copy the connection command. In a terminal window, run the command in a Python virtual environment that has the trainML package installed and is configured for your account. Once it connects, by default, you will see the workers' logs output to your terminal as they progress. When the workers finish, they will automatically upload the contents of the output folder to the directory you specified in the job form. When they finish uploading, they will automatically stop and billing will stop. We can unzip the output files and see the saved checkpoint files as well as the train.log file for each worker. If we open the training log file for each of the workers, we can see the final accuracy score for each model. As we've seen in this tutorial, trainML training jobs make it easy to run parallel model training experiments on GPUs. All you have to do is specify what command to run and what model code with which data and how you want to get the output, and trainML handles the rest. If you'd like to learn more, you can check out our documentation site at docs.trainml.ai or shoot us an email at sales@trainml.ai. If you run into challenges running this example or anything else, you can always contact us at support@trainml.ai. Thanks for watching.